All right, our last section for chapter 10 here, we are going to run some hypothesis tests on our standard deviation. Just a reminder that for standard deviation, we use the chi-square distribution. Here is the formula where you take your degrees of freedom times your sample variance divided by your population variance. And remember that this is the one that is not symmetric. It does change shape depending on how many we've sampled. As we increase the number in our sample, is going to become closer and closer to being symmetric. And remember that because we are squaring things, everything's going to be greater than or equal to 0. So just a reminder, we looked at this before. So you can see that as we increase sample from the red to the orange to the green, to this purple here, they're getting closer and closer to a normal curve. If we want to do a test on a population standard deviation, here's what we're going to do. Remember that our sample should be random sampled. Our original population should be normally distributed so that we can run our test. So our test will be set up again as follows, where the null is always our equals to statement, and then our alternate is either not equal to, less than, or greater than, depending on what it is that we would like to test. We will then get our level of significance to make sure we do not make our error. We will then get our p-value by using our StatCrunch technology. So we can check if p is less than alpha, because if p is less than alpha, we reject the null, that we can then state our conclusion. All of these follow the same process. The only thing we need to be careful about is this one. It is not considered robust. So we do very much need to know that it came from a normal distributed process. But just so you know, again, the ones that I give you in this class will be ones that you can complete. It will come from a general normally distributed set of data. The example from our Snickers bar, and I believe I still have that data saved from StatCrunch. We knew that we wanted to test if the mean weight of our fun size Snickers was 20.1 grams. Suppose that the standard deviation of the weight of the candy was 0.75 grams before the machine recalibration. The engineer wants to know if the recalibration resulted in more consistent weights. More consistent means that we have reduced our variability. So you need to understand that when you say more consistent results, that means less variability, which means less standard deviation. So we want to conduct the appropriate test at the alpha of 0.05 level of significance. Remember, we have our data table here. I will double check that mine is in StatCrunch here in just a second. Size Snickers, and I believe we had checked that one before we made a box plot. Let's see. Box plot for fun size, yes, we did conduct that. It was normally distributed, no outliers, so we can again run the test on this time with a standard deviation. We know that it came from a normally distributed data set. So we want to conclude that our standard deviation is smaller than 0.75 grams. 0.75 is what we had to begin with before the recalibration happened. We want to know, do my new values have less spread apart? Is that value smaller than 0.75? knowing that our level of significance is 0.05. Now, there's one thing we have to do here. When we use variance stats, we are testing the variance. It is setting it up in terms of the variance. Variance is standard deviation squared. So we have standard deviation. That is totally fine in how we write our hypotheses here. But there's one step that we have to do when we enter our values into StatCrunch. Because when I pull up my test here, it's going to ask me for my variance. I only have the standard deviation. So it says right here, note that the variance must be entered, which is taking 0.75 and squaring it, or taking 0.75 times itself. This is the value that is entered into your hypothesis. So when I go here, to run a variance on my sample, I have data. This is variance, not standard deviation. So I cannot just type 0.75. 0.75 is my standard deviation, or the square root of the variance. So I need to make sure I square that value to know what I enter here, which is 0.5625. Oops, I got an extra decimal in there. And then we are testing less than. These results were on the slide. I just wanted to make sure you saw how I did it. So here's our p-value, 0.3022. If I compare that to alpha of 0.05, that is bigger. So p is bigger than alpha. We do not reject the null hypothesis. If we do not reject the null hypothesis, we do not have enough evidence to conclude that the standard deviation is less than 0.75 grams. The recalibration made sure to keep our means the same, but our spread, it didn't change anything to do, it didn't affect our standard deviation at all. Machine fills bottles with 64 fluid ounces of liquid. The quality control manager determines that the fill levels are normally distributed with a mean of 64 ounces and a standard deviation of 0.42 ounces. That's what we know. We start with a standard deviation of 0.42. And a mean. So I guess as I'm reading this, I don't know which one it is yet. So I kind of have to keep reading. I know we're in this section, so we're using standard deviations. But the next sentence will show you that we're doing that test. So he has an engineer recalibrate the machine in an attempt to lower the standard deviation. So that right there is telling you, okay, we are testing standard deviation. We want to lower the standard deviation. We want that to be smaller than, I don't know why I just clicked, or 6.442. After the recalibration, the quality control manager randomly selects 19 bottles and finds that our sample standard deviation is 0.38 ounces. Is there less variability in the filling machine using the value of 0.01 level of significance? Before I run this test, though, I need to make sure I calculate the variance value. So we have 0.42, and I have to times it by itself. My variance is 0.1764. Variance is 0.1764. So that's something else that you should calculate for your hypotheses here. StatCrunch, stat, variance, one sample. This time I have a summary. I need my sample variance. I need to do that as well. My sample standard deviation was 0.38. So 0.38 times 0.38, my sample variance is 0.1444. Variance 0.1444. Okay, oops. So my sample variance 0.1444. Sample size, it was 19, right? Yes. And that was 1764 here. And we wanted to test, what did we test? Less than. All right. So I'm going to click compute. And I'm going to get my p-value here. So 0.3199. If I compare that to alpha 0.01, well, that is bigger. E is greater than alpha. We do not reject the null, which means we do not have enough evidence to claim the standard deviation is less than 0.42. I cannot make that claim. All right, so 0.42 to 0.38 is not enough of a difference in terms of the spread. And it looks like the calibration on this machine did not really make an impact on my standard deviations. We got one more example here. Waiting in lines. This problem is from 10.3. We didn't do it in 10.3, but it's repeated here in this section 10.5. This is the mean waiting time at the drive-thru of a fast food restaurant. The manager is worried about the variability in his wait times. Prior to the new drive-thru system, the standard deviation of wait time was 18 seconds. We knew original standard deviation was 18 seconds. Use the data in the following table to decide whether the evidence suggests the standard deviation of wait times is less than 18 seconds. So we want to test, is it less than 18? Null, alternate. So the first thing I'm going to do is I need to square that. So basically just means take 18 times 18 in a calculator. Variance is 324. We have data, so we don't have to worry about writing any of our information here. We're just going to type that data into StatCrunch. And we are going to use alpha of 0.05. So p-value, alpha is 0.05. Let's open our StatCrunch. All right, so this is wait time. Our wait times are 108.5, 67.4, 58.0, 75.9, 65.1, 80.4, 95.5, 86.3, 70.9, and 72.0. 1085, 67, 58.0. And that's why we double check these. 75.9, 65.1. Okay. We're good there. So I'm going to go to stat, variance stats with one sample. This time I have data that is called wait time. And my hypothesis, the squared value is 324. And I want to know, is it less than that value? If you want to make sure, we can make that box plot really quick. So if I scroll to the second page here and look at my box plot, I have no outliers, so I am good. And then I can look at my p-value. My p-value here is 0.303. 0.3 is clearly bigger than 0.05. So when p is greater than alpha, we do not reject the null. And if we do not reject the null, we do not have enough evidence to claim the standard deviation of wait time in the drive-through. I cannot spell today. Drive-through, THRU, is less than 18 seconds. All right, that is hypothesis testing. Those are all the hypothesis tests that we will be conducting here for one sample: proportions, means, and standard deviations. As always, if you have questions, you get stuck on something, please do not hesitate to reach out and ask me questions. I can do some extra examples, whatever it is that you need. But you guys are good to go on to the rest of your assignments for this week.